Well, good morning, everyone. According to my clock, it's 9 a.m., which is a scheduled start time for this morning's webinar on soil salinity, soil sodicity, and managing salt-affected soils. We've got a lot to talk about today, and we already have some questions that were submitted with the registration. So we think there will be a fair bit of interest in our topic today. So let's get into it. I'm Dr. Alan Blaylock. I'm Senior Agronomist for Nutrien. I'm based in Colorado. Been with the company for approximately 25 years and have worked really across the United States and Western Canada, as well as some international work. And much of my career has been spent in the Western US, where this topic is certainly of interest. We have a lot of challenges with this issue. Formerly, I was an extension specialist with the University of Wyoming. One of the most frequent questions I would get would be how to deal with soil salinity problems. So let's get into this. So many of us in the West have seen pictures like this. It looks like snow, but those are really salt accumulations on the top of those plant beds. And you can see there's very little plant growth where that salt has accumulated. We'll talk about why that occurs. It occurs in low-lying areas where we have water tables close to the surface. We'll talk about why that happens. And in these areas, only the most tolerant plants will grow. Here you see wild barley, which is a very salt-tolerant species. In some of these areas, that's a plant that we commonly see. We also see it where we have seepage, drainage water accumulating, bringing salts to the surface. So just some examples of the kinds of things that we see. Now, oftentimes we don't see the salt at the surface to the extent that these pictures are showing, but those of us in the West are familiar with these. So there are a few specific problems, and we'll talk about several of these. First is the problem of total salts, and total salts really cause an osmotic effect on plants. They interfere with water uptake, and so that effect is what we're trying to remediate. The second problem we have is where we have high sodium in the soil, particularly exchangeable sodium, and that sodium causes permeability problems, physical problems with the soil, infiltration, crusting, poor aeration. And we'll explain how we deal with that as well. Sometimes there are some specific ion toxicities, though these are probably less common than the first two problems. They may occur in certain situations. And in some cases, some of the chemistry caused by soil salts can change nutrient availability, affect nutrient balance. There may be concerns about corrosion of metal that is placed into soil, tillage implements, things like that. So where do these salts come from? First of all is natural mineral weathering. Minerals, as they weather, release salts into the soil solution. This may occur over geologic time. I'll give you an example of that on the farm that I grew up on and what we did about it. Shallow or perched water tables are often a cause of salt accumulation in the soil. Upward capillary flow brings the salts to the surface, the water evaporates, the salts stay in the soil and the water leaves, and so thereby over time the salts can become concentrated. Irrigating with poor quality water. Now what we mean by poor quality water is water that contains excess salts, and these can be a variety of things, but it's usually chlorides, sodium salts, carbonates, bicarbonates, sulfates. So and high pH of the water can also contribute to some of these problems. So these are the things that we would look for in irrigation water. And as we add water to the soil, the salts tend to be concentrated again. The plant uses the water, water evaporates, the salts remain behind, and so over time can become concentrated if we don't maintain appropriate leaching. Soil amendments and fertilizers over time can result in salt accumulation. Usually, this is not a major source of salts because the rates of fertilizer are much lower than these other sources of salts that I've talked about normally. They can be problems placing fertilizers too close to the seed. That's a salinity effect. Use of manures especially can contribute to salt accumulation in the soil. Manures contain some degree of salts, and if we're using high rates of manures, particularly over long periods of time, and again, not maintaining sufficient leaching to keep those salts moving out of the soil, then that can result in soil salinity. And basically, high evaporation rates, evaporation and or transpiration of water out of the soil in excess of the water that's being applied. So in the West, that's natural. We have much less rainfall than the amount of evaporation. So that's why we get the accumulation of these salts much more commonly in drier regions, arid, semi-arid regions, than we do in humid regions of higher rainfall. So here's an example. It's a very simple illustration of how these salts come to the surface as the soil wicks water up through the profile. The salts in that water are carried with it. Just remember, the salts go wherever the wetting front goes. And so as that water moves up to the surface, we see a higher concentration typically at the soil surface, a little bit of a bubble, as it were, right at the water table. And if that water table is closer to the surface, this effect will become exaggerated. If the water table is deeper, then those salts often don't make it to the surface, and it's not really a problem. So the first thing we need to do, and this is, as is the case with many problems, we have to identify specifically what the problem is, because there are different types of salinity problems, and the corrective action we take is highly dependent on the type of problem we have. We can actually make a bad problem worse if we follow the wrong order of treatments or do the wrong things. So we want to identify what that is. Here are a list of some of the key soil tests that we would need to have to take that corrective action. First of all, pH. Now, pH indicates mineral solubility. It can be an indicator of high sodium in the soil. It's one of the classifying characteristics, as it were, that we use to characterize what the the salinity problems are. Electrical conductivity of a saturation extract. This is another key test. And this is done specifically on a saturated paste. So it's a special test that is used to characterize soil salinity. The soil is saturated in the laboratory. It's allowed to equilibrate, and then we siphon off, or we suck off the water from that paste and analyze the conductivity of that. And that's the measure that is used for salt concentration in characterizing saline soils. The units are in what's called decisiemens per meter, simply a measure of conductivity. And this works because those salts are what conduct electricity through water. Pure water doesn't conduct electricity, but we need those ions in solution. Formerly, it was expressed as millimos per centimeter. Mos is simply an expression of conductivity as well. It's the inverse of ohms, which is another expression of electrical resistance. We also need to know about the cation exchange capacity and exchangeable cations. We need to be able to determine the percentage of exchangeable sodium, or ESP. And in order to do that, we need to get the cation exchange. We need to measure the other exchangeable cations, and then we do some calculations to indicate that sodium hazard. If there are concerns about specific toxic elements, we need to be testing for boron, chloride, sodium concentration may be an issue there, and other things. And there sometimes we'll be interested in the presence of lime in the soil, how much free limestone there is, what's the bicarbonate, carbonate content of soil and water, are there high levels of sulfates or nitrates that may be specific concerns. So these are the basic soil tests we're looking for. Some of these may be included in a basic soil analysis that you might submit for nutrients, but generally most of these would not be, and so they would need to be requested. Most labs know how to run a saturated paste, particularly in Western North America. It's very common. The labs in the Eastern US may not routinely run those. So it's a test that you'll want to request specifically in most cases. So once we get some of these values, this is how we calculate a sodium hazard. Sodium as a percentage of the exchangeable cations. So we simply take exchangeable sodium over the total cation exchange, divide that and multiply by 100, and this gives us the exchangeable sodium percentage. Another measure that is sometimes calculated, it's not exactly the same as exchangeable sodium percentage, but expresses a similar relationship, and that is the sodium adsorption ratio. The formula for that is given here. We take the exchangeable sodium and divide it by the square root of the sum of exchangeable calcium, exchangeable magnesium divided by 2. And that gives us the sodium adsorption ratio. Now, the sodium adsorption ratio can also be used to calculate the sodium hazard for water. So if we're doing an irrigation water test, we would use the sodium adsorption ratio, where the exchangeable sodium percentage is only applicable to soil. So here's a table that gives the basic classification for the different categories of salt problems. Now, so we'll walk through this and look at the different parameters. So a normal soil, so non-saline, would be a soil that has a pH of less than 8.5. And this is because in most soils, the carbonate, bicarbonate, calcium buffer system governs the pH. The equilibrium pH of lime in water is 8.3. So until we have something else driving the pH up, the pH will stay below about 8.5, and many soils are actually much less than that. In Wyoming, where I was working, we had a lot of soils in the high 7s, low 8s, pH 7.8 to 8.2 or so. So they were soils that had free lime present controlling the pH. Here we have electrical conductivity in decisiemens per meter at less than 0.2. Now, I will say, I've modified this from what you'll find in many publications. Many publications list the threshold as 4 decisiemens per meter rather than 2. In some of the literature more recently, authors have proposed that this threshold be lowered to 2 because there are many of our crops that will show yield reductions at salinity levels or electrical conductivity levels below 4.0, and have proposed that this be the threshold. And so I'm using that lower threshold because a lot of our common crops will be affected at this level. And then we have, in the normal soil, we have a low exchangeable sodium percentage or low sodium adsorption ratio. In a saline soil, the pH is still low, lower than 8.5, but the electrical conductivity is higher. And again, this is a reflection of the total salts, but not dominated by sodium. In a sodic soil, now the pH goes up, and this is now because as sodium increases in the soil, sodium starts to displace calcium at high enough concentrations, and that causes the formation of bicarbonates and hydroxides, which drive the pH up. And as the pH goes up, calcium becomes less soluble, calcium carbonate is precipitated, and so we have a higher ratio of sodium to calcium, and the higher the pH goes, the more exaggerated that becomes. The electrical conductivity is lower because we don't have high total salts, but we have high exchangeable sodium, and that's reflected in the exchangeable sodium percentage, high SAR. And then there are types of soils where we have the combination of high salts and high sodium. The salts tend to buffer the pH less than 8.5. They tend to counteract the effects of the sodium, but the high salt is reflected in the higher conductivity, and the sodium is reflected in the exchangeable sodium percentage. The true sodic soils are probably the least common of these three. Saline soils, fairly common. Saline sodic soils may be a bit less common. But oftentimes when we have high total salts, we also have some presence of sodium because it's one of our most soluble minerals. So anyway, this is the classification that we use. And we want to understand this before we embark on remediation procedures, because the remediation pathway we take will be determined by the categorization of these soils. And if we were to treat a saline sodic soil incorrectly and just assume it's saline, start leaching the salts, then it could become a sodic problem, which is much more difficult to correct. So how do salts interfere with water? Well, those ions attract water molecules and compete with the plant for the water molecules. And this is just an illustration of that. You see the water molecules are now bound to these salts in the soil solution. And so they're increasing what we call the osmotic potential of that solution. And when that exceeds what the plant, the osmotic potential of the plant, then the plant is unable to get water. So we have a question here about this categorization. Why not call a soil as normal if it is neither sodic or saline sodic? There is hardly any need then to talk about these properties. So yes, a normal soil is not included in the description of saline soils, but we're using the normal soil as a comparison. We're using the normal soil as our baseline. These properties of low conductivity, slightly alkaline or acid pH, and low exchangeable sodium as being the comparison to which we want to relate the saline or saline sodic soils. Now, one thing I should note before I move on from this is that keep in mind that these are on a continuum. The soil doesn't suddenly become or take on sodic properties at 15% exchangeable sodium, where at 14.9 it doesn't have any of those properties. Keep in mind it's a continuum. We can see the effects of salts or sodium at levels below this. This is just a system of classification, but keep in mind that in all cases it's a continuum, and the problem gets gradually worse as the levels of salts or sodium increase. Okay, so managing saline soils. Let's talk about our practices here. The goal is to maintain an acceptable yield or productivity, and that means we have to maintain adequate moisture for growth. And because the salts are interfering with water uptake by the plant, that may mean we have to maintain different soil water content. It may mean the plant is more stressed when water is less available. And there's no real chemical amendment to neutralize or remove these salts. There's nothing we can add to deactivate these salts, as it were. The only real solution we have is to remove the salts from the root zone, or we can change crops to something that's more tolerant. Now, in order to do that, we have to maintain a sufficient leaching fraction, or at least over the course of a growing season. We may not have to maintain a leaching fraction in every irrigation, but over the course of the growing season, we need to make sure that there's more water passing through than is being evaporated and transpired. Sometimes we can switch crops to something that's more salt tolerant, and there's a wide range in crops. We'll show some examples of that. And I'll also illustrate some different planting configurations we may be able to use to place seed where it's less likely to be affected by the salts, away from the salt accumulation. So we'll look at that a little bit as well. But really, it's a leaching challenge. And in order to maintain leaching through the root zone, we have to have good drainage. Keep in mind, often the source of these salts is a high water table or a perched water table. And so we have to correct that in order to create any permanent solution. So in terms of crop tolerance, we can look up the sensitivity of our desired species, and there's lots and lots of publications with this information, with long lists of crops and their ratings, and there's been much research done on this, keeping in mind that many species are more sensitive to salts during their germination and emergence. And a crop I worked with in Wyoming that was of concern was sugar beet. Sugar beets are listed as a salt tolerant crop, but I can tell you from personal experience that during the germination and seedling stage, they're quite sensitive. Once they're established, they're very salt tolerant, but as a seedling, they're not. And we also need to consider the economics of managing the salt effect. Can I accept a 10% yield reduction due to soil salinity or water salinity? Can I accept a 20% yield reduction? So we have to weigh the potential yield reduction against the cost of remediating the problem. If the problem can't be remediated economically, then I may have to accept a lower economic yield, or maybe a crop that's less economically viable. So here's a chart that has been widely used over the decades, published in a FAO paper number 29, which is one of the references that I use all the time. It's been around for a long time, but the data is still accurate. The science hasn't really changed that much. And so it simply shows an approximate yield reduction for different classifications of crops at different salinity levels. So down here we have the ECE, which is the salinity of the saturation extract that we mentioned. Here's the electrical conductivity of irrigation water. So we can also use this for tolerance of problem irrigation waters. And so I can look at this and say I take a moderately sensitive crop at about a 20% yield reduction, I can tolerate an EC in the soil of about 5. And so above that, the yield is going to be further reduced. If I want a higher yield level, then that same crop, for that same crop, I'm going to need to be at a soil EC of maybe around 1.5 to 2. So this helps us estimate the economic loss that we may observe for different levels of correction. And so this is kind of valuable, and we can use this in relation to tables that categorize the sensitivity of the crop. Now, this is a short list. This is again taken from that same FAO paper. Again, I've used this many times over many years, and so you can see some of the thresholds for different crops. And you look at barley, which is one of our more salt tolerant crops, and even at an EC of 18, which will kill just about everything we plant, we can still produce an estimated 50% yield potential. Cotton, the numbers aren't listed here, but cotton's a fairly salt tolerant crop. Sugar beets, as I mentioned, sorghum is fairly salt tolerant and sometimes used as a reclamation species. Then we go down here to some of our more sensitive crops like maize, and this is edible beans, Phaseolus vulgaris beans, some of the more sensitive crops that we grow. So if we look at maize as kind of an indicator crop, and this is one of the reasons that I suggest using a threshold EC of 2.0, because at that level, corn is going to be showing some yield reduction. So that's why I suggest using that lower level as opposed to 4.0. Soybeans is an interesting crop here in that the yield reduction or the salinity level that causes a given yield reduction doesn't change much across the range. So so what this is showing is there can be a very sharp drop off in yield with a small increase in salinity. Its threshold is a little bit higher than, say, corn, but its tolerance doesn't increase as much from low to high. So that's kind of an interesting one. But cereal grains are usually some of our more salt tolerant crops once they're established. All right, so excuse me, there are two kind of types of salinity problems. One is that results from shallow uncontrolled water tables. In other words, either a perched water table or a water table that's close to the surface. The correction for this has to include drainage. As I mentioned, we have to lower the water table. If it's If that water table is at the surface because of some impermeable layer in the soil, that has to be broken up somehow so that drainage can be achieved. We may have to install artificial tile drainage or create perimeter drainage ditches to remove that excess water. And once we create the drainage, then we have to maintain this leaching fraction. But if we don't create the drainage first, the excess water doesn't help us. The other source of these problems could be poor quality irrigation water. As we mentioned, these problems are usually worst at the surface. So the farmer is more of a geologic issue. It's a problem with the physical nature of the soil, the land that we're dealing with. Poor quality irrigation water is applied on the soil surface. The salts tend to accumulate, remain at the surface. These are usually less serious problem as long as we have adequate drainage again, and we need to analyze our irrigation water. We can deal with certain levels of salinity if we maintain adequate drainage and adequate leaching. These problems are usually a bit more readily remediated than something that's in an inherent property of the soil itself. So let's talk about leaching of salts. So first, what we mean by that is maintaining a net downward flux over the growing season. I may alternate leaching events with alternating irrigations, or I may leach before I plant the crop to remove the salts and leach during the off season. Now, keep in mind that we're talking about leaching salts. And when we leach salts, some of those salts are also plant nutrients. So we're trying to balance the need to remove hazardous salts against the need to keep the beneficial salts, the plant nutrients, in the soil profile. So we have to think about coordinating our particularly nitrogen management with our salinity management and say desynchronizing those or decoupling those. We want to coordinate that leaching with the rotation. So for example, if I'm rotating a sensitive crop with a tolerant crop, maybe I don't need to do the leaching much, if at all, on the tolerant crop, but I can leach during the off season before going into a sensitive crop and maintain that leaching fraction for that crop. And that allows me to save on water over the whole crop rotation. Leach at times when it's more effective. The cool season, for example, when we don't have as much evaporation and we can more easily push water through the soil more efficiently. Before planting or after harvest when there's not a crop growing. Because these leaching events can also result in excessive soil wetness that may not be beneficial to the crop. Reducing tillage and using residue covers to reduce evaporation. There's kind of mixed feelings on cover crops. Cover crops certainly help infiltrate water and they help build soil quality, which is also helpful in managing these problems. But cover crops also increase the evapotranspiration and may make it more difficult to push water on through the soil. So just kind of keep in mind that balance. So here's how you calculate a leaching fraction. So you would use a figure like the one we previously showed. You would identify the tolerance that you're after. So what's the electrical conductivity of the extract that I'm searching for? What EC in the soil am I willing to tolerate given the yield potential that I want? And then I have to integrate that with the electrical conductivity of the water, because if I'm using more saline waters, it's going to take more water to prevent salts from accumulating. And so then I plug the electrical conductivity of the water and the soil into this equation, and it calculates a fraction of water in excess of evapotranspiration that I would need to apply. For example, if I'm going to need 3 inches of water, for example, for a certain period of time on the crop, and my leaching fraction is 10%, I would have to apply 3.3 inches of water to achieve that 10% leaching fraction. So that's simply how that would be expressed. It's telling us the percent of water in excess of crop demand that I would need to apply to push it past the root zone. And so this is how that's calculated. Again, in this FAO paper, there's lots and lots of formulas and cookbooks for how to do some of these things, but this is a critical factor in reclaiming saline soils. There may be some ways we can improve the efficiency of that in terms of the amount of water we need, alternate ponding and drying. It takes longer to move the salts out, but less total water. We can apply water at rates less than the infiltration, maintaining unsaturated flow. It's more efficient because saturated flow largely goes down the large pores, where unsaturated flow can also leach salts out of the micropores because it's moving through the aggregates as well. So that can be more effective leaching. Slowing overland flow, so things that we can do to prevent water running off, more water going into the soil as opposed to running off, and that means crop residues. Tillage can decrease preferential flow by breaking up the open channels and increasing roughness, reducing runoff, but that reduced tillage can also enhance infiltration. So there's a trade-off there, and also thinking in terms of long-term soil quality and building soil organic matter, which will also greatly help infiltration and the ability to maintain that leaching fraction. So there's certainly a lot of benefit to building soil quality in this as well. Now, I just want to say a few words about irrigation uniformity in terms of remediation. If our irrigation is not uniform, and these are a couple of aerial photos of some center pivots, and you can clearly see that there are distinct irrigation patterns in these two circles. How effective, how uniform is our reclamation going to be if we have salinity problems in this field? And we may indeed have problems that are a result of non-uniform irrigation. So the effectiveness of the reclamation is only going to be as good as the quality of our irrigation and our uniformity. So keep that in mind. There will be a profound influence of that remediation practice. Excuse me. Okay, so a few of the things that we can do, and keeping in mind that oftentimes, once we get the crop established, it will have a higher tolerance than that young seedling. So there's a variety of schematics proposed, and this is simply some illustrations from a Pacific Northwest Extension publication that I'm using here. These illustrations are found in a lot of different publications, but so here we have different salt concentrations, and it's showing you where the salt accumulates in different planting configurations. So this rounded top hill, the salts will accumulate in the center near the top of that hill. In a flat top hill, they're spread out a bit more, because there's a bit more surface area where they accumulate. So the concentration is spread out a little bit more, but it's spread across the entire bed. And then if we look at a double row bed, a double row bed, and we have plants on either side of the row, the plants on the edge of that bed are in a lower salt concentration than the plants in the middle, because keep in mind, the wetting front is going to be, and this is with a furrow irrigation system, the wetting front is going to move from the water furrow into the bed, and it's going to evaporate up out of the bed, and the salts accumulate in the center. So by planting on the edge, that seedling has exposure to a lower salinity level. Here's a couple other configurations that have been suggested for dealing with that. If we plant in a rounded bed and we create a notch in the center, the salts are going to accumulate around that notch. And then we plant the plants away from that notch to move them away from the salt accumulation. Or planting a plant on one side of a flat top bed and only watering on that side, which pushes the salts beyond where that seedling is planted. So again, exposing those plants to a lower concentration. So there's a variety of things we can do with irrigation and planting configurations to help that plant get started. Now, here's an example of drip irrigation and the salt effects around the drip line. Now, drip irrigation is often designed to apply lower amounts of water over a more constant period of time. And so when we look at a couple of different soil textures, on the left is a sandy loam soil, and on the right, the clay loam soil, and we look where the drip line is and where the salt's accumulating. So the salts are the yellows and reds, and if we look where the drip line is, the salts are accumulating approximately midway between the drip. That's where the wetting front would be. So water is moving downward below the drip line, particularly in this sandy soil, and so it maintains a fairly low concentration below the drip line. But in between the drip lines is where the salts accumulate. So if I'm planting a crop that is sensitive to salts, do I want to plant it between the drip lines or on the drip lines? So you can make your own judgment on that. And then here in the clay loam soil, we have a bit less leaching going on. So we have stronger gradients. There's more accumulation near the surface, less movement of salts down, but you still see the accumulations are at the wetting front between the drip lines. Here's another example of drip irrigation, and it's the top figure is where we have sufficient water to leach salts down, and the bottom figure is where we don't have sufficient water. So particularly this would be a concern if there are salts in the water. And so if we're maintaining sufficient leaching, we can keep the salts moving away to the sides and down from the drip line. But if we don't apply enough water, the salts continue to accumulate around that drip line because we're not moving them far enough away. So what we do with our irrigation and planting configurations can greatly influence the susceptibility of plants to the salts. Okay, so let's talk about sodic soils. Sodic soils are some of our most difficult soil problems to correct. We have to have drainage, but the effect of sodium on the soil is to slow infiltration, and we'll explain how that happens, but sodium interferes with drainage and somehow we have to correct that. Excuse me. We have to supply a soluble source of calcium to displace that exchangeable sodium. So there are some options that we have there, but we have to determine the nature and the source of the problem. Where's the sodium coming from? If it's coming from irrigation water quality, then we have to deal with that. That is mainly going to affect the soil surface and sealing of the soil at the surface. And there are also water table problems, much like total salts. These generally affect the entire soil profile. The sodium may be of geologic origin. The farm I grew up on in Eastern Oregon, we had a strongly calcareous subsoil. There was caliche and lots of free lime in the subsoil, but above that was a layer, a sodic hardpan that was a function of the formation of that soil over thousands of years. And that sodic hardpan prevented water infiltrating into the soil. And so we really had problems irrigating. And I'll explain what we did to fix that here in a bit. So here's an illustration of how that occurs. A flocculated soil, the aggregates are sticking together. There's lots of macropores. Water moves freely through that soil. But when we have sodium, a high percentage of sodium on the exchange complex, it disperses those clay particles. The soil pores clog and the water ponds on the surface, and it's difficult to get the water to move past that. Okay, so we need to review just a moment the concept of cation exchange. Soil clays are negatively charged. They attract cations or positively charged anions, including sodium, calcium, magnesium, hydrogen. But the two that are most prominent in this relationship that we want to talk about are sodium and calcium. Magnesium will be somewhat similar to calcium in its behavior. So we'll talk about sodium and calcium. Now, it's important to keep in mind that sodium has a very large water shell around that molecule, and that kind of repels or pushes the clay particle a bit farther away. Calcium has two charges and a small water of hydration, so it has a much higher affinity for the clay particle and tends to pull them tighter together and flocculate those clays. And so this becomes important in the remediation of sodic soils. We want to get rid of this sodium. We want to exchange it with calcium. So we have to supply a form of calcium to increase the calcium in the soil solution and force the sodium out. So we may have to change water quality. If we have high sodium in the water, that's not going to be good for the long term. And if we do have high sodium in the water, it's going to be an ongoing problem that is not going to be fixed with a single remediation event. We can add water amendments, acid forming materials or soluble calcium to the water. And acids are viable if we have lime in the soil from which calcium can be released. We can add soil amendments. So for example, gypsum, sulfuric acid or acid forming materials, other soluble calcium salts to maintain infiltration at the soil surface from that poor quality water, and anything we can do to improve soil permeability, the surface of the soil, like reduce tillage, cover crops, deep rooted crops, anything we can to keep water moving into the soil, because infiltration is our limiting problem there. If the problem comes from an uncontrolled water table, in other words, the sodium is coming up from the water table, it is throughout the profile. Now this is going to be a bit more difficult. We have to have drainage, then we're going to have to remove that sodium. So the first thing we do is somehow correct our drainage problem, lower the water table so that we remove that source. Then we have to add our calcium and or acid amendments. Now I say acid amendments because if the soil has lime in the soil, there's calcium there, but it's not soluble. We have to bring that into solution, and adding an acid can dissolve that lime, bring that calcium into solution where it can exchange on the complex with sodium. Working the soil when it's dry. Now, if we work the soil when it's wet, that can make the problem worse by smearing and compression of the soil. So we need to work it when it's dry, where we can shatter those sodic layers. We have to incorporate the amendments fairly deep, get them down to where the sodium is so that that calcium can exchange for the sodium. Adding organic matter can be extremely helpful. Large volumes of materials such as manures can be helpful here. And coarse fibrous materials that are slow to decompose, corn stalks, wheat straw, any of those things that decompose slowly but yet open the soil up. Fine materials that tend to clog the soil are not going to help us out as much there. So maintaining that soil organic matter is really helpful. I actually saw a study, and I was looking forward in preparation for this. I could not find it, but years ago, I ran across this study where some researchers had used for remediation. They had planted a salt-tolerant sorghum Sudan grass, and the deep-rooted nature of the crop plus the acids produced in the root system were actually almost as effective as adding gypsum alone, and doing the two together was the most effective treatment. So one of the problems with these soils is the challenge of growing plants in a soil that is sealed off, it's poorly aerated, we can't get water in. So if we can get anything to grow, anything at all to grow in that soil, it will help with the remediation, particularly in these more severe cases. And we may have to adjust our water application rates because the soil is sealed off, we can't get water into it, so we may have to irrigate at a lower rate, at a slower rate, in order to get the infiltration we need. So our process here: increase the drainage, add calcium to displace the sodium, and then leach the sodium out and do what we can to open the soil up. So let's talk a little bit about amendments. The calcium flocculates the soil clays. The gypsum generally doesn't really affect nutrient availability. We're talking about high rates here, and it's tons per acre. sometimes many tons per acre for remediation. Calcium chloride is a highly soluble and effective salt. It's much more soluble in gypsum, and some of the studies I've seen with calcium chloride say it takes less because of its higher solubility. However, the presence of applying high rates of chloride may limit the safe rate, may limit how much you can apply and still be safe. Same with calcium nitrate. We don't want to over apply nitrogen. However, the calcium in calcium nitrate is very soluble, very effective at exchanging for sodium. It's just a matter of getting enough out there. So how does this work? Just an illustration. Here's what I'll call a dispersed soil. I've illustrated these little rectangles as our soil particles. I apply calcium sulfate. I add water. The calcium sulfate dissolves. The calcium, because it has a higher affinity for the clay particles, kicks those off. They can then be leached out the bottom. The bottom of the profile, the calcium flocculates the clays, improves the permeability. So simple illustration, that's what's happening. Maybe not always so simple to achieve in practice, but and certainly the economics of this are problematic in that we're talking about tons of gypsum to apply, plus the difficulty of the physical remediation of these soils. So we have a question coming in about the economics of this. These are sometimes not economical problems to fix. They're very expensive to fix, and it can take time. This probably isn't done with one application of gypsum in one growing season. It may take years to really reclaim one of these soils. So I mentioned our farm that we had in Eastern Oregon, and we had this Sodic hard pan down about 18 to 24 inches to 36 inches maybe. And below that was this is not a picture of our farm, by the way, but it's a picture of what we did on our farm. So we had this strongly calcareous subsoil underneath that sodium hard pan. So what they did, when we did the whole farm, basically, we went in with these big moldboard plows. Now, they call this deep plowing, and this isn't deep plowing as in 24 inches. This is deep plowing as in 3 to 4 feet deep. And so what that did was brought up that calcium in the subsoil, broke up the sodium hard pan, mixed the calcium with it, and then the calcium dissolved and displaced the sodium, and the farm was much better for decades after that. This was done back in the 60s and made a huge difference in our ability to properly irrigate and farm that land. Okay, let's talk about acid amendments briefly, and then we'll try to wrap this up and allow for some questions. So acid amendments. Now, when we talk about acid amendments, some people think about sulfuric acid on sodic soils. A lot of people use elemental sulfur. These are good ways to improve calcium solubility in the soil. The effectiveness of this amending the soil in this way is dependent on the presence of free lime in the soil. If we don't have free limestone in the soil, then adding more acid isn't going to bring more calcium. So, but if we have lime in the soil and we add acidity to dissolve that, remember, one of the effects of sodium is to drive up the soil pH, which lowers the solubility of calcium carbonate. So by adding an acid or acid forming material, we dissolve the lime, bring the calcium into solution. That calcium then can displace the sodium, and then we can leach it out. So the effect is essentially the same as adding a soluble calcium material. So anything that produces acidity in the soil could be beneficial to remediating a sodic soil. So sulfuric acid has been used at times. It's sometimes used as an irrigation amendment. There are formulations like Infuric, which is a product that we used to sell. It's simply a solution of sulfuric acid and urea, sometimes used to purge drip irrigation lines, but can also be used as an irrigation water amendment. Elemental sulfur is easier to handle. It's more economical than sulfuric acid. And believe me, sulfuric acid is pretty nasty stuff. I've worked with it in laboratories and, using it to dissolve soil organic matter, and it's nasty stuff to handle. So it requires special equipment and extreme care. Elemental sulfur, dry material, comes in various forms, much easier to handle. The reaction is a bit slower, obviously, because that sulfur has to convert to sulfate, and in that process produces acidity. So it can be a very effective remediation treatment for sodic soils if there's free lime present. Any of the thiosulfate fertilizers are also acid forming. Ferric sulfate produces acidity in the soil. These materials would be applied at low rates because of their cost, and would be considered much more expensive than elemental sulfur per unit, because keep in mind, we're talking about tons. We're not talking about a few pounds per acre. We're not talking about elemental sulfur as a crop nutrient here. We're talking about enough elemental sulfur to change soil chemistry. And so that's usually on the order of tons per acre, not pounds per acre. So how much do we need to apply? Well, here's a formula for determining how to calculate that gypsum requirement. Exchangeable sodium over the calcium or the cation exchange capacity gives us that exchangeable sodium percentage. We simply look at what's our desired ESP. If we're starting at, say, 15 and we want to get it down to 10, we multiply that by the cation exchange, take the difference, multiply by the cation exchange, multiply by 1.7, and that gives us our gypsum requirement in tons per acre. So fairly simple calculation, but we have to know the cation exchange capacity and the exchangeable sodium percentage, both starting and where we want to get to. Now, so this is given in gypsum requirement based on pure gypsum. If the material is less than pure, then we'll have to increase the amount accordingly. Here's a table that just gives you some different roughly equal values for different materials. For example, here's elemental sulfur. So if we say the requirement is 1 ton of gypsum, we can do the same thing with 0.2 of a ton of sulfur. If our gypsum requirement were 5 tons per acre, we would need a ton of elemental sulfur to achieve the same result. And you can see some of the other materials here listed. Calcium chloride, calcium nitrate being very effective, but obviously the limitations we've talked about. So again, for all of these, it assumes that we have pure fine materials and that calcium carbonate is present in the soil to dissolve. All right, so let's talk about the saline sodic soils. Our approach here is fairly simple. We treat it as a sodic soil. Because the salts in the soil tend to keep the clays flocculated and help maintain infiltration, we do not want to leach those out until we've provided a source of calcium to displace the sodium. We have to displace the sodium before we leach. Doing the reverse can turn it into a sodic soil. If we leach the salts first and leave the sodium, now we have a sodic soil, and that's more difficult to deal with. So we want to displace the sodium first, then leach. So just treat this as a sodic soil and avoid turning it into a sodic soil. All right, so here's a schematic that I took from one of the oldest references on this. It's called Agriculture Handbook 60. It's still in use today in many places. There's lots and lots of detail on chemistry and procedures and calculations, and it's one of the standard references. It was published in 1954, but the science in it is still good. Anyway, without going through this whole schematic, so you start with your soil sample and you say, do I have a permeability problem or do I have a salt problem? And you work through all of these schematics, and in the end, everything boils down to a leaching problem. Everything boils down to not having good drainage. So if I have salinity problems, it's likely because I have drainage problems. Too much water, poor internal drainage, poor permeability, all of those things that we've talked about. So summary, know the problem. You have to sort out which type of soil problem I'm dealing with. Is it salinity? That's remediated by salt leaching. Is it a sodic soil? That's remediated by displacing the sodium, then leaching. Is it a saline soil? That's saline sodic soil. That's remediated in the same way. I have to know the irrigation water I'm dealing with, because oftentimes it's part of the problem. And if I don't have irrigation, if I'm under natural rainfall, I'm at the mercy of nature to help me with this. And that means it may be very difficult to remediate those problems. And I may have to work with more tolerant crops or different cultural practices or other remediation practices. And that means some of the land, if I don't have irrigation to remediate, that means some of the land may not be usable the way I want to use it. Know the crop, because they vary widely in their salt tolerance, and there are lots of resources available for that. And be patient, because the remediation of these problems can take years, sometimes decades. It's not often that you can do what we did on our farm and go in with a big plow and all of a sudden everything's nice. It doesn't usually work that way. So with that, I think I'm posting some references here. I will add that the presentation has been recorded, and all those who registered will get a notice when that's available, so you can come back and find these references. I found this extension publication. It's published by Oregon State University, but it was a cooperative effort of the Pacific Northwest states. I found this particularly helpful. There's lots of good information there, and without a lot of the more difficult math and chemistry, maybe some people don't want to deal with. But this first one I listed, like I said, is one of my Bibles, so to speak. A variety of other resources, so you can look those up at a later time. We hope that this has been beneficial for all of you who attended, and we appreciate you attending. So if there are no further questions or comments, we will end this webinar and say until we meet again.